Greetings everyone. I am S.V.UDAY Sharma from the Triply Department of Institute of Aeronautical Engineering. Today, I am going to discuss about the topic applications of vector identities. Application of vector integrals in fluid dynamics. To find the rate of change of the mass of a fluid flows. Since the fluids are not rigid like solid parts, the fluid body can move in different velocities, and fluid does not have the same density all over the body. We can find the total mass in the fluid region by integrating the density over R. Triple integral of R, rho of x comma y comma z into dx dy dz. If the region R is not changing with the time, assume that R is control volume or fixed volume. Only way the mass is going to change is by the fluid entering the and leaving the R through its boundary surface M. If we let if we let v x comma y comma z comma t be a time dependent vector field, which the v will give the velocity of any point, we can say that the flux integral of rho v over m will give the rate of change of mass flow. dm by dt is equal to triple integral of m rho v n ds. So we can see the vector integration is used in finding the rate of change of the mass of a fluid flow. Stock theorem. Calculate the circulation of a fluid of a closed curve. Stock theorem is used in this. The application is circulation of fluid about a closed curve. Why this? This is the just the time integral v over y, which we can rewrite for any surface m which has y boundary. Double integral of m delta into v and ds to analyze the vorticity of the fluid body. As the Wikipedia says, vorticity is a pseudo-vector field that describes the local spinning motion of a fluid near some point, or the tendency of something to rotate, as would we see by the observer located at the point and traveling along with the fluid as the fluid dynamics. Here we can see in this picture absolute vorticity. The orange indicates minimum and the purple indicates maximum. In here, the Stokes theorem is used in calculation. It states that the circulation about any closed loop is equal to the integral of normal component of velocity over the area enclosed by the counter. Integral v dot dt is equal to double integral of a into delta v to n dA. Berkner's circulation theorem. To analyze sea breeze. In fluid dynamics, circulation is a line integral around in a closed curve, the velocity field. It is obtained by taking the line integral of Newton's second law for a closed chain of fluid partial. It is known as the Berkner's circulation theorem. Integral of dv by dt is equal to minus 2 omega into v minus 1 rho delta rho into gf dt. This theorem uses vector integration. This theorem is used in analyzing the barotropic fluids. The definition of the barotropic fluids is that they are useful models into fluid behavior in a wide variety of scientific fields, from meteorology to astrophysics. Most liquids have a density which varies weakly with pressure or temperature, which is the density of a liquid, is nearly constant. So to first approximation, liquids are barotropic. The sea breeze analysis can be explained using a barotropic flow. Sea breeze will develop in which lighter fluid, the warm land air, is made to rise and the heavier fluid, sea air, is made to sink. So the air we see is come to land with the free land to fill the free place. This occurs sea breeze. Application of vector calculus in electricity and magnetism. In the discussion, we will discuss the mathematical consequences of theorems. Let us take electric and magnetic fields in space of E x comma y comma z comma f and B x comma y comma z comma t, where xyz represents the position in space and t represents the time. Further, let rho x comma y comma z comma t be charge density and the j x comma y comma z comma r the current density in space. Current density is a vector field sign since current is given by both magnitude and direction. The equations governing electricity and magnetism are delta into E is equals to rho by E naught, epsilon naught, Gauss law. Delta into E is equals to minus of dp by dt, Faraday's law. Delta into B, delta dot B is equals to 0. Delta cross B is equal to mu naught J plus mu naught epsilon naught rho E by rho Ampere Maxwell law, where epsilon naught is equals to 8.85 into 10 power minus 12 c square by nm square is the permeability of the free space, and mu naught is equal to 4 pi into 10 power minus 7 n into s square by c square is the permeability of free space. Magnetic field B is always solenoidal and can be written as a curl of a vector potential B is equals to delta into A. Thus, we can show that the magnetic flux throughout any closed surface is always zero by using the following theorem. Here we can see the electric and magnetic fields. The theorem is vector field F is three-dimensional space said to be solenoid or incomposable if any of the following equivalent conditions are true. Delta dot F is equal to 0 at every point. Double integral of M F dot n ds is independent of the surface M having the same boundary curve. Double integral M F dot n ds is equal to 0 for any closed surface M. For any vector potential A, F is equal to delta cross A. Since the divergence of any curl is 0, we can write using Maxwell's equation delta dot into delta cross E is equal to delta dot minus rho B by rho B is equals to minus of rho B by dot T into delta plus delta cross delta dot B is equal to 0. For the magnetic for the magnetic field, we get delta cross B is equal to delta dot mu naught J plus mu naught epsilon naught dou E by dou T. Delta cross B is equals to mu naught delta dot J plus mu naught epsilon naught dou by dou T into delta dot E. Delta cross B is equals to mu naught into delta dot J plus dou P by dou T. The consistency of divergence of curl to be 0, it is required that delta dot J plus dou B by dou pi is equals to dou P by dou pi is equals to be 0. Now, let us consider constant electric E and magnetic field B. Then these two time derivatives get dropped out of Maxwell's equations. In this case, the curl of electric field is 0. Thus, we can write E is equals to minus delta phi, where phi is some scalar potential function, phi x comma y comma z. The minus sign is used for the easiness. Thus, we can represent the flow of positive charge from higher potential point to lower potential. In this constant field over a closed path, the cyclic integral evaluates to 0. Now we have delta dot E is equal to minus delta dot delta phi, that is equals to minus delta square phi, that is equals to rho by epsilon naught. When the object is highly symmetric, we can use Gauss law and Ampere's law to calculate electric and magnetic fields. Consider a uniformly charged solid sphere of radius r. Since there is no any preferred direction from symmetry, we can say that electric charge outside the sphere is radially directed, which only depend on the radius r from the origin. So E dot n is equal to E dot E into r. because the electric field is parallel to the normal vector. Now we can integrate both sides of Gauss law over a solid sphere b pi of some constant radius r greater than capital R and use the divergence theorem. Triple integral of br delta dot e dv is equals to triple integral of br dou by epsilon naught dv is equals to q by epsilon naught. Double integral of me dot n ds is equals to double integral of m e into r ds, that is equals to 4 pi r square e into r, where q is the total charge of the sphere, e into r is a constant on the sphere of radius r, and rho is a constant in the charged sphere and 0 outside it. We can do analogous calculations for magnetic fields. Suppose we have an infinity long thick wire of radius r. Current is flowing throughout this cylinder with some uniform current density J. Now, because the force on a moving charge due to direction of the field, symmetry tells us that the magnetic field due to this infinite wire must be tangential to circles perpendicular to and centered on the wire. That is, if you point the thumb of our right hand in the direction of the current, the field lines go around the wire in the direction of our fingers. By symmetry, the magnitude of the magnetic field depends only on the perpendicular distance r from the wire. Now we integrate both sides of Ampere's law over a solid distance d, that is of some constant radius r greater than r using Stokes' theorem. Double integral dr into delta cross b ds is equals to double integral dr nu naught j ds is equals to nu naught j nu naught I. Phi r b dx is equals to phi r b into r dr, that is equals to 2 pi r br, where I is a total current through the wire and j is a constant in the wire and 0 outside it, and b into r is a constant of the circle radius r. Thus we see b into r is equals to nu naught I by 2 pi r. It is same as a magnetic field due to infinitely thin wire, which current I inside the wire with the field and slightly complicated. As a final illustration of this use of vector calculus to study electromagnetic theory, let us consider the case where the fields and times varying, but we are in free space where the charge and current densities are both zero. We will need to make use of the following identity for a vector field f, which can be easily provided by writing down the definitions and checking each component. Delta cross f is equals to delta into delta cross f minus delta square f. We apply this identity to both electrical and magnetic fields and use all the Maxwell's equation to simply the results. Remembering that both rho and j are assuming to be zero, delta cross E is equals to delta into delta dot E minus delta square E. That becomes minus delta square E. That is equals to minus delta into minus dou B by dou T. That is equals to minus dou into dou T into delta cross B. That implies minus nu naught epsilon naught dou square E by dou T square. And similarly, dou cross B is equals to delta cross B is equals to delta into delta dot B minus delta square B. That is equals to minus delta square B. That is equals to delta into epsilon naught nu naught dou E by dou T. That is equals to nu naught epsilon naught dou by dou T into delta cross E. That is equals to minus of epsilon naught nu naught d square dou square B by dou T square. Thus, we see that each of these components of the both electric and magnetic fields satisfy the differential equations dou square f by dou T square is equals to c square dou square f. For c is equals to 2 by root of, for c is equals to 1 by root of nu naught epsilon naught. This equation represents the motion of the wave with speed c. Hence, we see that is free in space. The electric and magnetic fields propagate as wave with speed. 1 by nu naught epsilon naught is equals to 1 by root of 4 pi into 10 power minus 7 nb square into 8.85 into 10 power minus 12 c square by nm square. That is equals to 2.99863 into 10 power 8 meter per second. This is the exact speed of light. Maxwell studied an electromagnetic waves and was able to deduce that the light is electromagnetic wave upon the extreme information of light back in 1880 LH in 1818. All electromagnetic waves, gamma rays, X rays, ultraviolet rays, light infrared rays, microwaves, radio waves are propagating electric and magnetic fields. The only difference in the frequency from wave to wave is different. They all travel at the same velocity. The energy of the wave is proportional to the frequency, which is why X-rays far more harmful to us than radio waves. On the application of vector identities. Thank you. This is Uday Sharma signing off.